So, we are going to continue the same discussion and in this class also. In the last class I just told you that there are 3 different types of intermediate phases exist in the binary phase diagrams, which normally forms by periodic reactions, but there are other types, other reaction also which can lead to formation of these intermediate phases. So, but most of them actually forming by periodic reactions. That is the reason I brought this whole thing into the periodic reaction, periodic phase diagrams as a part of that. So, I told you that there are 3 types of intermediate phases. First one is valency type, second one is size factor type, and third one is the electron compounds. Okay. So, first one is basically like a sodium chloride structure or calcium fluoride structure. They are stabilized by the valence electrons. So, there is a transfer of valence electrons from outer shell to one atom to the other atom, and then the bonding happens. But second one, which is stabilized by size factor, for which I will show you some structure details in the slides, but they are called Lewis phases, and there are 3 types of Lewis phases. One is called MgCu2, which is cubic structure, MgZn2, which is hexagonal structure, and MgNi2, which are called hexagonal structure again, but double unit cell of hexagon. It will be very clear to you when I show you the slides, and I gave you examples of those compounds. Third one, which we are discussing in the last class, but we could not finish, is the electron compounds. They are called Hume rotary phases because they are discovered by Hume rotary, and these compounds are stabilized by E by A ratio, where E is the number of valence electrons, total number of valence electron compound, and A is the total number of atoms in the compound. So, there are specifically 3 ratios only in which these compounds can form. One is 3:2, second one is 21:13, and third one is 7:4. These all have come from copper zinc phase diagram. Specifically 3:2 is known as beta brass, 21:13 is known as beta brass structure, 21:13 is known as gamma brass structure, and this is known as epsilon brass structure, 7:4. Okay. And therefore, they do exist in the copper zinc phase diagram. Okay. You have probably, if you look at detail, their composition, that these are existing. So, beta brass has a BCC structure, crystal structure. Gamma brass is also BCC unit cell, but with 52 atoms in the unit cell. It is a large BCC unit cell, and this is hexagonal system or epsilon brass, correct. So, I have given you 3 examples: CuZn 3:2 ratio electron by atom, Cu9Al4 21:13, and Cu3Si 7:4. Before actually we do these different kind of phases, let me just give you the valencies of different elements. How do we are decided? Okay. So, valencies of different elements you need to know. This is very important. It is better you take it down when you are listening to this lecture. So, let us suppose elements and number of valence electron. Correct, number of valence electron. So, our element or elements. So, let us for copper, silver and gold, number of valence electron we consider to be 1. Then for lead, magnesium, zinc, cadmium and beryllium 2. Third one is aluminum, gallium and indium 3. Tin, silicon, germanium 4. Antimony, arsenic, phosphorus, bismuth, not phosphorus, bismuth, antimony, arsenic and bismuth 5. And last one is Pt and tungsten metals, okay, 0. Tungsten metal means like iron, cobalt, nickel. There is no, we do not consider valence, there is any valence electron. Okay. So this table you should remember, you better take it down, because you need to calculate 3 different ratios, then we need these values. That is what I wanted to give you at the beginning, so that you do not forget. So now it is very easy, copper and zinc. Okay. As you see, zinc exists somewhere, yes. So copper 1, zinc 2. So for copper zinc there are 3 valence electrons, copper is 1, zinc is 2, and there are 2 atoms, so 3 is to 2. So copper and aluminium, 4, copper has 1 electron, so 9 into 1 is 9, 9 into 1 is 9, plus 4 into 3 is 12, so this is 21, and number of atom is 9 plus 4, 13. So here again copper silicon, number of atoms are 3 plus 1, 4, number of valence electron, copper has 3 into 1, 3 into 1, silicon has 4, 7, 7 by 4, very easy, anybody can do these problems. So now let us look into the different compounds after I given you the table, different compounds of different types of series of that, and let me just remove these things to show you. Only thing I will keep is this table, so that it helps you to understand. And suppose I will tell you copper aluminum system, copper aluminum and or silver aluminum, it exists. So this is Cu3Al, we will calculate again, Cu9Al4 I have written already, and this is Ag3Al, correct, 3 plus 3, Ag3Al, Ag3Al3, no, this is, so what will happening, 3 plus 12 is wrong, it should be different, something is wrong there. So it was okay, Ag3Al was fine, Al3Ag, 3 plus 1 is 4, 3 plus 1 is 4, 7 is not coming, so it will be 3, yes, 3 plus, this is 4, so 3 plus 3, 7 plus 7, correct. So now this is copper silicon, Cu5Si, Cu5Si, Cu is 5, 5 into 1, and 6, say silicon is 4, so 5 plus 4 is 9, 9 and 6, 9 is to 6 is 3 is to 2, okay. How 9? Cu is 5, 5 plus 1, 4, 9, and there are 6 atoms, 9 by 6 is 3 by 2, okay. So you can clearly see that taking place. Now this one is Cu31 silicon 8. So Cu31 is 31 into 1 plus 8 into 4, silicon has 4, okay. So that means 31 plus 32, 63, and how many? 39 atoms. 63 is 39 is 21 by 13, correct. Okay, last one is Cu3Si, this I have already discussed, correct. Now for the last, yeah, that is enough. So that these are all different examples of these valence compounds which forms by the reactions. It is very clear that this table is what is going to help you in calculating the ratios of different compounds, correct. Okay, let me just also give you some more examples, and like one example I will give you here is Cu3Ga. Cu3Ga will fall under which one? Which category? Whether T is to 1, T is to 2, 21 is 13 or 7 is to 4, let us see. Cu has 1 valence electron, so 3 into 1, gallium has how many valence electrons? Ga 3, so 3 into 1, 3, so 3 plus 3 is 6 and 4 atoms, 3 by 2. This is a 3 by 2 compound, very clearly you can see this will fall under bitter brass. So what about Cu3SN? Cu3SN? Cu3SN is, Cu is 1, so 1, 3 into 1, Sn is how much? Sn is 4, so 4. So 3 plus 4 is 7, and 4, 7 by 4, so that is epsilon blast, the last one type. And then okay, I have probably given Cu Zn, this is Cu is 1 plus Zn is 2, therefore 3, and number of atoms is 2, 3 by 2. So these three are these two Cu3Ga and Cu-Zn, they have different compositions. You can see one is 75% copper, 25% gallium, other ones 50-50 compositions, but both of them are of same type, C by 3:2 type, that means they have a BCC unit cell with beta bar structure. That is the major discovery of Hume theory, that these compounds, although they have different compositions in the phase diagram, they are coming at different positions in the phase diagram, but they have similar crystal structure, and these crystal structures are BCC or BCC or beta bar type. I hope that is for these electron compounds. So let me just go back to the slides now, and let me show you interesting things about size factor compounds. Okay, I told you there are three different size factor compounds. One is MgCu2 type, and another one is Mg. So there are three types of size factor compound: MgCu2 type, which is cubic, and MgZn2 hexagonal, and third one is MgNi2, again hexagonal. There are three types. So first one, let us show. All of these are stabilized by size differences of the phases. The crystal structure of MgCu2 is shown in this slide, where Mg atoms are bigger atoms which are sitting at the corners of the cube, also at the face centers of the cube, correct. This is a face center cubic structure. But on the other hand, copper atoms are sitting at the alternate tetrahedral voids. You know, there are 8 tetrahedral voids inside a FCC unit cell. So therefore, there are alternate tetrahedral voids. You see here, this is filled, bottom one is not filled. Here bottom one is filled, top one is not filled. Similarly for these two. And these tetrahedra are formed by copper. There are 4 atoms in each tetrahedron. Okay, 1, 2, 3, 4. 4 atoms in each tetrahedron, correct. So how many atoms will be there? 4 into 4, 16 atoms of copper. And how many atoms are present for the unit cell, FCC unit cell of magnesium? 8. Okay. How many? 1 plus 3, 4. Okay. But you have to understand that out of these 16 atoms, 8 atoms are out of for the unit cell, other 8 are not. So that is why it is 8 by 4, that is why it is Mg2, MgCu2. Cu is 8 atoms and 4 atoms are magnesium. So this is the first type of structure, and there are many compounds like TiB2, AgBu2 and BiAu2, they forms this compound. Next one is MgZn2. MgZn2 actually basically forms such a kind of hexagonal structure, and they are also stabilized by tetrahedral atoms, and you can see here A atoms are the bigger atoms which are shown here, B atoms will be shown in the next slide, whereas MgNi2 is a same hexagonal structure only, but unit cell is doubled. Instead of x plus y, it is x plus 2y, it is x plus y plus z, x plus y plus x plus z, doubled, where z and y are same almost. So this is this, and now let us discuss about these tetrahedral coordination. You can see here for MgZn2, MgNi2, again tetrahedrali coordinated zinc atoms are stabilizing this compound. Here tetrahedrali coordinated copper atoms are stabilizing this crystal structure, that is why it is called MgCu2. Here tetrahedrali coordinated zinc atoms are stabilizing these structures. Here tetrahedrali coordinated nickel atoms are stabilizing this structure. Okay. So this is, therefore these structures are stabilized by stacking of tetrahedra in these structures. So now I have shown you that there are different coordinations. Okay, tetrahedral coordination, tetrahedral coordination, tetrahedral coordinations, but they can have the coordination numbers obtained from this also is possible. So there are different types of coordination possible, that is what I am saying you. It is not only that you have 8 coordination or 12 coordination possible, you can have 14, 15, 16 coordination possible, and they are known as Frank-Caspar phases, which exist in different phase diagrams. Just to introduce you, I am showing it. This is CN12, coordination number 12, which is same thing like FCC structure. FCC has a coordination of 12. Every atom is coordinated by 12 atoms. But if you have a little bit distorted structure of that, okay, you can see here this is pentagon on the surface, you can have a coordination number 14, or even more distortion will lead to coordination number 15. Central atom is coordinated here by 15 atoms, or you can have 16, you can see, correct. So, normally CN13 is known, does not exist. CN13 is for the icosahedral structure, which is not part of this. So, that is what actually it does not exist. And I also like to tell you that these compounds which I showed you in the earlier, other than this, they are very useful, correct, like Mg12Zn13. This is a very, it forms a eutectic with alpha, this eutectic it forms with alpha, and this has a spiral structure. And now yes, now this one, sorry, this one Al3AP, they are all used in the intermetallic compounds in the high temperature applications, Al5AP2 or Al3AP. Al3AP is widely used, and I told you that Al2Cu, Al2Cu eutectic, this eutectic is very classical eutectic, where many alloy system has that. And aluminum copper is a duralumin is a material which is used for the aerospace applications, and in that this eutectic exists. And then you have an aluminum nickel is a classic system in which all of them are used. AlNi has a very high melting temperature, it can be used. On the other hand, Al3Ni5 or sorry Ni3Al or Al3Ni, they both are used for many applications, especially Ni3Al used in the turbine blade applications. So, with this I have given you that the phases which forms by the Peytectic reactions, and I told you that there are phases which exist in the phase diagram which does not form by Peytectic reactions, which forms by congruent melting. Okay, let me just explain that congruent melting stuff. Okay, now I just take this diagram to explain you. Congruent melting means when a compound melts, its composition does not change when it becomes liquid. Let us take example of AlNi, and it has 50% nickel, 50% aluminum 50% and nickel 50%. Okay. So, when it melts directly to the liquid, the composition of liquid will be exactly same as the solid, and that is why it is called congruently melting, compound. It forms directly from the liquid with the same composition of the liquid, right. So, these congruently melting compounds are exist in many phase diagrams. This is one such. There is another one I showed you here, aluminum silver. What is that? The aluminum silver AgMg, it also forms by congruent melting. You can see this is forms directly. So, if this compound melts, it will become liquid will have the same compositions, correct. But on the other hand, things which are forming by Peytectic reaction, let us suppose this one, okay, Mg, or let us simply use the aluminum nickel system, that is much easier here. Okay, let us suppose this one Al3Ni, it forms, Al3Ni is forming by, this is the phase field of liquid, this is a liquid plus Al3Ni2. So, therefore, liquid plus alpha liquid plus Al3Ni2 reacting Peytectically to form Al3Ni. So, now if I heat this one, so that means if I see the reverse reaction, if I heat this Al3Ni, what will happen? You will have this solid will form another solid of different composition, Al3Ni composition, and the liquid. So, therefore, liquid will never has the same composition as the solid, and these are called incongruently melt compound, incongruently melting compound. Okay, these are called. So, thus there are two types of these intermediate phases as far as the melting is concerned. One is congruently melting like AlNi, which directly melts in liquid without change of compositions, and there are compounds which melts by periodic reactions when it heated up. So, therefore, liquid has different composition than the solid at the start with. Periodic phase has this composition, liquid has completely different composition than this, because there is another solid phase forming, and they are called incongruently melting compounds. So, with this I think I have completed all the important parts of intermediate phases. In the next lecture I am going to talk about monotectic phase diagrams, and monotectic and syntectic are the phase diagrams which are distinctly different from what you have seen so far. And before actually we do that, I will show you a few experiments where liquid phase immiscibility is demonstrated, and then I will go ahead with the monotectic reactions. Thank you.